So this is going on page 120 when we are done. We're going to be talking about bearing again. Bearing's not brand new. We first talked about it when we did law of cosines, directions, which are our angles, and then what our resultant force is. So as far as vectors are concerned, the direction of a vector can also be given as a bearing, and bearings are frequently given in application problems because that's just kind of the real world part of it, and it's a capital beta is what we usually refer to with bearing. So we have two different types. This is a reminder. We have what's called a quadrant bearing if we have some sort of direction attached to it. So this, so we'll call this bearing 1. So our south 60 degrees east right here, this is bearing 1. A true bearing is the angle measured clockwise from the north. Clockwise, you start at true north and you go clockwise. So the true bearing of this vector to the right is 120 degrees. This is 120, and we'll call this bearing 2. And that's how and here's the other part of this. True bearings are written with 3 digits. So 120 obviously is 3 digits. But if you have a true bearing of 15 degrees, you write it as 015 degrees. Okay? A little additional information there. So bearings are all fine and great. That's how you talk about it in the real world. That's how things would be discussed. But when we're actually calculating stuff mathematically, we don't use our bearings. We use theta. And theta is always measured from 0 on the x-axis around. So what would the angle of this vector be for theta? Or how can I find it? 270 plus 60, right? Which will give us 330 degrees. So mathematically, what we would use in our calculations is 330. We could talk about it as 120 or 60, depending on how we talk about the quadrants. But in the end, theta is what we need, and that's 330. Okay, that makes sense? All right, so let's look at these here. It says for each vector, give the quadrant bearing and the true bearing. So for number 1, they give us this 85 degrees. This is theta. Okay, so they gave us theta. As a quadrant bearing, would I start from the north or the south? The north, because I'd go up first, right? So north, and then I would swing out this way, right? How much would I swing out? 5 degrees, north, 5 degrees, then what? Which direction did I go? East, okay? So as a quadrant bearing, that is north, 5 degrees east. As a true bearing, I start from true north, which is kind of what I did anyway, and then I go clockwise, so it's still 5 degrees, but since it's a true bearing, we use 3 digits, and it would be 005 degrees. Okay, so I'd either say it's on a bearing of 005 degrees or a bearing of north 5 degrees east. Just depends on what kind of format it's in. All right, on number 2, once again, they gave me theta. The quadrant bearing, would I start from the north or the south? The south, okay? So I'd go south, and then I'd swing out this way. So how can I figure out how much that is? 270 minus 212, that's one way. I mean, there's different ways to manipulate it. So what would we get? What's 270 minus 212? 58. So south 58 degrees what? West. Okay. So this is 58. Another way we could have done it is 212 minus 180 is what, 32? And then I could have done 90 minus 32. I mean, that's a couple of steps, but if that's what makes more sense to you, there's nothing wrong with that. I mean, you got a calculator, you can figure it out. All right, so then my true bearing, start here and go around. How am I going to figure out what that is? 180. Okay, either 180 plus 58, or I heard somebody say 270, or I could do 270 what? Minus 32. Either way, like whatever makes more sense to you, doesn't matter either way. But what do we end up getting? 238. Everybody okay with that? Okay, so on number 3, they did not give us theta. So let's think about what theta is here. What would theta be on number 3? $90 plus 24, good. So 114. I know I didn't ask us for that, but we should be able to figure it out. So our quadrant bearing, do I start from the north or the south? North. And then I swing out 24 degrees. That's basically what it gave me. And then what comes next? West. Okay. My true bearing, I start here, go all the way around. 360 minus 24. So 360 minus 20 is 340. Subtract 4 more, I get 336. Any questions about that? Because if we can't figure that out and we don't understand how those all work together, that makes the rest of this kind of impossible because we have to be able to get our thetas. We good? All right, so still dealing with vectors, still doing the same kind of work we've been doing. Our magnitude, which could be length, it could also be speed, which we're going to have magnitude of speed. Could be a force. I mean, it could be a lot of different things. So on number 4, we have an airplane flying at a bearing of 245. So let's deal with the bearing first. If our bearing is 245 degrees, it means to start here, 245 ends up somewhere over here, right? Oh, that's 245. 45. I need theta, right? Theta starts here and goes this way. So I wouldn't directly use 245 in either way. I would say I could either do, so this 245, I could do 245 and subtract 180. That would give me 65 right here. And then I could do 270 minus 65. That works, right? Or I could do 270 minus 245 and get 25 right here. And then I can do 180 plus 25. It doesn't matter either way, but whatever we do, we get that theta is not 180. It is 180 plus 25. It is 205 degrees. Okay. Any questions on how we got 205? So it gives us a bearing, but the theta we're going to use is 205. Okay, so now that I've done with that, I'm going to mark out 245 so I don't use it by accident. And so it's flying at a bearing of 245 at 550 miles per hour. So that is my magnitude. I want the velocity. So there's a difference between speed and velocity. Speed is just how fast you're going. Velocity also gives you a direction. So give the velocity of the airplane as a vector in component form. So that means that my velocity vector is equal to the magnitude, or the speed in this case, 550 times the cosine of theta, which is 205, and 550 times the sine of 205. So that's my vector in trig form, but it's asking for it in component form, so I have to actually push buttons to get the answer. So go ahead and get your velocity vector. We will get and your vector is negative, negative, which should make sense because your angle is here in the third quadrant. What questions do you have? Okay, so just because these are application problems doesn't mean that you always get bearing as an angle. Here it says a man pushes a lawnmower with a force of 25 pounds, so this force is our magnitude here. And it says uphill at an angle of 40 degrees. So I'm just going uphill at an angle of 40 degrees. that 40 degrees is my theta. Okay, it's not a bearing, it's not anything else. I'm just going uphill at 40 degrees. My theta is 40 degrees. So if I want it as a vector in component form, my vector is going to be 25 pounds of force times the cosine of 40, and then 25 pounds of force times the sine of 40. And since our angle is in the first quadrant, we would expect the A and the B to both be positive. If they're not, then something went awry somewhere. Any questions on that? Okay. So, number 6, a cruise ship is sailing at 20 knots in the direction of north 12 degrees west. Give the velocity of the cruise ship as a linear combination. So we're going to start off by finding the component form and then go from there. But the first thing we need to do is they gave us this bearing, and so we need to figure out what that is as a theta. So I'll give you a second, bless you, for that to happen. So figure out what your theta would be here. (102 degrees? You agree with that? Okay, good. So then my vector is going to be 20 knots times the cosine of 102, and then 20 knots times the sine of 102. And we would expect the signs, the SIGNs here, to be negative positive, right? Bless you. So we get component form, but it does ask us for this as a linear combination. So then we can very easily translate that and make that negative 4.158 I hat plus 19.563 J hat. Okay. What questions do we have? Okay, so one thing that happens in math a lot is that we have application problems that are real-world problems that don't always have all the real-world things in them. For instance, if a cruise ship is sailing at 20 knots, and at this specific direction, there's more things that are affecting the cruise ship than its speed, right? There is current, there is wind, there's all kinds of things that could be affecting the direction it's actually going, right? And so we're going to add some of those forces in there when we flip it over. It says if two or more forces are acting on an object, then the resultant force is the sum of the two vector forces or more vector forces. So let's look at number 7. 2 tugboats are pushing a barge. If tugboat A is traveling in the direction of south 80 degrees east, tugboat B is traveling in the direction of north 65 degrees east, and both boats are pushing at a force of 400 pounds, find the magnitude and direction as a quadrant bearing of the resultant force of the barge. So they're both pushing with a force of 400 pounds, so it makes sense if there was 800 pounds of force being applied, but there's not. Let's look back at what we have. Tugboat A is traveling in the direction of south 80 degrees east. So we're just going to do kind of a rough little sketch over here. So south 80 degrees east and say, it will look something like that probably. There's vector A. Okay. And then B is traveling at a direction of north 65 degrees east. So it would look something like that probably. Again, it's totally fine that it's not super accurate here. And then when I add them, this is what I get. This would be vector A plus vector B. Okay, so that's my resultant force. So it looks like I'm looking at probably a first quadrant angle, even though it's just kind of a rough sketch. You don't have to sketch that every time. I just wanted you to see, again, we're literally adding vectors. Even though the tugboats are not attached in that specific way, that's what's happening with the forces. So we're going to need this A plus B here. So we're going to start off with vector A. And we're going to need to figure out what theta is. So for vector A, or tugboat A, it's traveling in the direction of south 80 degrees east. So south 80 degrees east. This is 80 degrees, right? So then I need theta. What would theta be? 270 plus 80, so 350 degrees. We agree with that? Okay, so for tugboat A, we can call it vector A. That is going to be, so we have a force of 400 pounds, and then not using that, I'm using the 350. So I have 400 times the cosine of 350, and 400 times the sine of 350. Then we're going to pause there. We're not going to push buttons on the calculator yet, because I need to deal with vector B. So vector B, we are traveling here, north 65 degrees east, north 65 degrees east. So this is 65, which means that theta is what? 25 degrees. Okay, so not using that. All right, so for vector B, I have 400 pounds times the cosine of 25 and 400 pounds times the sine of 25. Now remember, what we want in the end is A plus B. So I'm going to need to find vector A plus vector B. And remember, when we add vectors, we just add the x components, add the y components. Again, before you start pushing buttons. When we do this, we're not going to be done. I need to then find the magnitude and the direction. So I'm going to have to use these pieces, and they're not going to be pretty numbers, so we're going to have to store them. And even though I called these vectors A, vector A and B, I could have called them anything. But usually my result here, it's going to be some vector that's AB, regardless of whether or not I'd called them an AB. Usually that's the way we do it. So we can store them in A. So you're going to do 400 times the cosine of 350 plus 400 times the cosine of 25 and store it in A. Shift, recall A. Don't push the alpha button. Okay? If you actually did all this stuff the last time we stored stuff, you actually did your assignments, and you actually knew what you were doing on your test, you should be able to store this stuff just fine. So you're going to get this number, store it in A, and you should have 756.446. And then add these two together, store them in B. 9.588. If you don't store them and you just retype the decimals in, your answer is going to be wrong. Just going to throw that out there. Store the x components in A, store the y components added together in B. Okay, good. So now that I have my new vector, this is my resultant vector. I need the magnitude, which it asked me for, and the direction. So magnitude of A plus B is equal to the square root of A squared plus B squared, and you can type it into the calculator just like that. Of course, your A's and B's are capital in the calculator, but it doesn't matter. It's the same thing as long as you store it correctly. And you should get 762.973. And what do you think the units would be on this? What were the units on the force to begin with? Pounds, okay? And so that 400 and that 400 acting on those angles, I didn't get 800, but I did get 762 something pounds. Oh, there's not two of those. Pounds. There's my magnitude. Okay? What questions do you have? Okay. So then I have theta. Theta is equal to the tangent inverse of B over A. That will give me alpha. And I think it gives it to you as a fraction, so you can use it as a decimal, and that's fine. What do we get for alpha? 7.5? And it's exactly 7.5. That's why we don't need 3 digits. Okay. What quadrant do we expect our angle to be in from this? First, because it's positive, positive. So alpha actually does equal theta. But it asked me for a quadrant bearing. So I need to think about what that means here. If this angle is 7.5 right here, my quadrant bearing, am I going to start from the north or the south? North. So I'm going to go north, and then I'm going to swing out this way. How much? 82.5. 82.5 degrees what? East. What questions do you have? Anything? Okay. So let's look at number 8. I have 2 forces with magnitudes of 85 pounds and 120 pounds are acting on an object at angles of 35 degrees and 140 respectively with the positive axis. Anytime you have an angle with the positive axis, that's just telling you it's theta, right? You started on the positive x-axis and you're getting theta. So it says find the magnitude and direction to the positive x-axis. So it gives us theta, it asks us for theta. So we don't have to overthink this, which makes this one fairly simple. So my first vector has a magnitude of 85 degrees, and the angle is 35 degrees. And then, so 85 times the sine of 35. And then I will just tell you, last period, it did all this, and I used 35 degrees twice. So it's not a bad idea once you use it to mark it out so you don't make stupid mistakes like what I did last period. And then, I should have called this vector 1. And then I can call this one vector 2. Then my force is 120, and my angle is 140. Like so. So then just like before, I need to find the magnitude. So, no, I don't want to do the magnitude first. I'm jumping ahead of myself, sorry. I need to add these together. Vector 1 plus, bless you, vector 2. And I'm going to get that component form. And I'm going to add the x components, store them in A, add the y components, store them in B. You could store them in X and Y. You can store them anywhere you want as long as you know what you stored where. So are we good with getting those components and storing them? Yes. Oh, I got my little vectors. All right, so once you do that, then I want you to find the magnitude of your new vector. This is going to be the square root of a squared plus b squared. And then I want you to find alpha and stop with alpha because we're going to need to talk about it. Tell me something that should always be true about alpha. It should be positive. Tell me what the calculator gave you. Negative, okay? And that's because I've told you, regardless of what you're putting right here, we always type in the positive, right? Well, here we stored a negative number, so we didn't have as much control over that. I mean, we could have controlled it. We could have made that like negative a right here, but that's a lot of overthinking. So I think, again, I think it's good to be consistent with what we do. So if you get this negative, and all we're dealing with here is tangent. So cosine was the weird one when we did inverses, right? But for sine and tangent, we were either going from 0 to pi halves, or 90, or 0 to negative pi halves, or negative 90. So what has happened, since we technically took the inverse of a negative number, it's put us down here. But it's just the negative of where we would really want to be. So we got a couple of options on how to handle this. It gives you negative 79 something, right? So we know then that alpha is technically 79.956, even though we have a negative number looking at us in the calculator. All we have to do is change the sign there. So then we need to ask ourselves, before we do anything else weird in the calculator here, what quadrant do we actually want theta to be in? We're looking at this. Second, right? Because we go negative, positive. So the vector could be anywhere, but it's going to be a second quadrant angle. What do we do with alpha to get a second quadrant angle? Subtract it from 180, right? So we could turn what we have in the calculator positive by multiplying by a negative 1. and then subtracting it from 180. But if it's already negative, then what can we do? Just add 180. You with me on that? And so theta, when you just add 180, which is like subtracting 79 from it, right? You would get 100.044. So whatever makes the most sense to you so you don't get confused. I think it's good to be consistent and alpha always be positive. So you can always multiply it by a -1 so you actually have your positive value in the calculator. And then take that and subtract it from 180. It's fine. But if you can reason through it, it's the same as just adding the negative. Either way, we're good. Okay? What questions you got? All right, so we're going to start number 9, but we're not going to do all of it. We're just going to look at finding thetas to make sure that, because this wording is different. So this says 2 cranes are lifting a statue. Crane A is pulling with a force of, we got crane A with a force of 600 pounds at an angle of 35 degrees to the left of the statue. Crane B is pulling with a force of 750 pounds at an angle of 50 degrees to the right of the statue. So here's what this means. So we have this, like that's the ground, I guess, and this is some statue, whatever it is. So if I was pulling the statue straight up, like if I could hover above it and grab it with the helicopter and just pull it straight up, it would look like this. Just straight up. But it's saying, but I have these cranes on either side of it. Crane A is pulling with a force of 600 pounds at an angle of 35 degrees to the left of the statue. So the left of the statue, that 35 degrees to the left of the statue, this is 35. And this is crane A. Then crane B is pulling with 750 pounds at an angle of that 50 degrees to the right of the statue, means the crane is pulling, that's what his vector would look like over here, and this is 50 degrees. And that would be crane B. Do you understand what it means by to the left and the right of a statue? That's what's going on there. Okay, I just want to make sure visually you get that. So then I want you to figure out what is theta for crane A and what is theta for crane B. So you get those while I hand out your worksheets, and then I will put them up there and we'll talk about them. All right, so what do we think theta for A is? 125. And what is theta for B? 40 degrees. Okay, does that make sense? And if you got that much, everything else is pretty much just the same steps. We good? Okay. I think the biggest challenge here really is just making sure you have the right theta. Making sure you've read the question and you know what's going on with the angles.